All right, let's take a look at an example of elastic potential energy. And so we're going to do this two ways. So let's go ahead and look at this question. It says a spring is 17 centimeters long and it's lying on a table. One end is then attached to a hook and the other end is pulled by a force that increases to 25 newtons, causing the spring to stretch to a length of 19.2 centimeters. What is the force constant of that spring? How much work was required to stretch the spring from 17 to 19.2 centimeters? And how long would the spring be if it had been stretched by a 50 Newton force instead of a 25 Newton force? So the two ways I want to look at doing this is the more graphical way and option 2, which uses our knowledge that we picked up last chapter in forces. All right. So the first thing we need to think about is drawing our picture. So we went ahead, I drew it 17 centimeters, and then we stretched it on that table to a little bit more, 19.2 centimeters, or 0.022 meters further than it originally was, using that 25 newtons. So the first way I want to think about this is graphically, because graphically the force is increasing to 25 newtons. So it starts at 0, and that force increases to 25 newtons. And I want to find out how much energy was stored. Well, all of that work that 25 newtons did got stored as elastic potential energy. And so essentially I can find that work that 25 Newton force did. All right, so I can find the area under this curve. So 1/2 of the base times the height gives me a work of 0.55 joules. But that doesn't tell me the spring constant. It's an easy way to find work, but I kind of bypass that whole knowing the spring constant part of it. So how would I find the spring constant? All right, so the spring constant is the slope of this line. Or thinking back to last chapter, that elastic force is equal to kx. So how much force is the spring applying? How far was it stretched? And the spring constant. So in our case, when it's been stretched 25 newtons, it is 0.022. So 25 newtons stretches at 0.022. And so I can go ahead and find that spring constant. Oop, I did not write that one down. So 25 divided by 0.022 gives me 1136. So 1,136 newtons per meter. Right? So I can find that spring constant, and then if I wanted to find this same amount of energy, I could talk about UEL as being 1/2 kx squared. And this will give me this same result of that 0.55 joules. So if I go ahead and I plug this in of 1/2 times 1136 times my x value, which was 0.022 quantity squared, I will get that same 0.55 joules. All right, and then lastly, part C says, how long will it be if it's stretched by a 50 Newton force? And that's where this graph kind of comes in nice, is that if I stretch it by 50 newtons, okay, so if I continue my spring constant being, yes, a spring constant, oh, almost made that, it moves out to this point here, so 50 newtons stretches it essentially twice as far, so a new distance of 0.044 meters. However, let's think about how much energy it took to stretch it that extra little bit. So if I think about this kind of graphically, I could kind of break this into essentially 4 little segments. So if I think about the total energy required to stretch it to 0.044 meters, a quarter of it was to stretch it the first half, 3/4 of it was to stretch it the rest. So if it took 0.55 joules to stretch it the first meter, it's going to take what? 1.65 joules to stretch it the next 2.2 centimeters. And it kind of escalates like that. And we see that escalation over here in this x term. So the further I stretch it, the bigger that energy is going to be. All right?